Okay, welcome everybody. Thanks for coming. This is the week 6 webinar. We're actually halfway done now. It's a 12-week class and we're in week 6. So we're in the middle and hopefully it's going well for you. And I want to let you know a few things. One is some of you may know is yesterday was a disaster. Do you guys know why? Maybe you don't. But Canvas, not just our class, but Canvas was down internationally, and AWS, yeah, Amazon, which hosts our class, and all of Canvas went down. So just happens. I didn't do it, I promise. But let you know that I had to get a little bit later start on grading a projects because it went down. But I've got about two-thirds of them graded now, maybe three-fourths even, pretty close. And so I'm getting there. And my plan is to finish tomorrow. I was hoping to finish today, but yesterday didn't happen. So so anyway, we're back up, able to do things. I guess Monday is one of the better days to have Canvas down because there's not too much going down in our class on Monday, but hopefully it didn't, hurt you guys too much. But anyhow, we're back up and things are good. And actually, I've been using Canvas for I think like 9 years or something like that. This is the first time it's gone down for more than 15 minutes. And it was gone for half a day. It was awful, almost all day long, actually. So, but we're back up. So I'm grading and, look at the comments. Um, One person submits, I write comments on the submission, and please, that person who submitted, please share it with your partner so they can see my comments because that is important. So that's one of your responsibilities on being the submitter is to share the comments, with your partners. I do want to mention one more thing, and that is it's too early to talk about Project 2, but what I can tell you is that just like Project 1, you are required to have partners. It's a disaster if you don't. It's pretty much impossible to have a passing grade. Um, even 50% is tough. So just let you know that you want partners. It's the same rule as Project One. You don't have to have the same project partners that you had in Project One, but you do have to have partners. And three is better than two, as always. So there is now a Project Two discussion post that you can pop in, discussion board that you can pop in and post if you're looking for partners. So that's just a note. And please do that. Do not wait 3 weeks from now to do that. Do it like in the next day or two. That's my strong suggestion. So let me tell you the plan for the day. So the idea here is always I'll answer any questions you have. And then really from today on, it's all applications. So that's the good news is that everything we do is used and it's all going to be applications. And this week, we're going to be looking at chapter 8, and that is confidence intervals. And we're going to break it up into confidence intervals when we have a quantitative data. So that means confidence intervals for means. Okay. And then we'll also look at when we have the yes no survey question, and we'll look at a confidence interval for a proportion. Then what we'll look at, and something we really haven't talked about too much, we talked about the central limit theorem. You need more than 30 to be able to use the normal distribution. But sometimes, even though you have more than 30, you may not have data that is close enough to the population mean for you to be satisfied. So we're going to be talking about how large a sample you need to have so that you can have data that you're really confident that your sample mean is going to be very close to the population mean. And then we'll do the same thing, but for proportions. So if you have how many yes, no questions do you have to ask if you want to make sure that the sample proportion is close to the population proportion. So that is the plan. I do want to let you know this is week 6. What's important about week 6? At this point, you all better know. What's important about the number 6? Yeah, no, 6 is an even number, so there is an exam this week. So, just let you know. On purpose, I make sure the projects are on odd weeks, so you don't have both in the same week. But there is an exam. And as always, like around half or so of the exam will be the first the stuff that you haven't done. So chapters 1, 2, 3, and 4. So you haven't done in a long time, and you haven't been examined on. You haven't had an exam on. And then the other part, and in particular the writing questions, will be on chapters 7 and 8. Okay, which is a central limit theorem and confidence intervals. So that's just a note in terms of what the exam is. So are there any questions about anything? Any questions? Okay. I do want to let you know I've been hearing more than one person, a group of people that are like complaining that, they're trying Sunday night and they don't have anything to reply to that they like. Strongly suggest don't wait until Sunday night to do a reply on the discussion post assignment. The longer you wait, the harder it is to find a good one to reply to. So don't be the last one. So that's a big suggestion. And also always make sure that your initial one is done by Thursday. Wednesday's even better, but by Thursday, because otherwise you'll lose points because it is due Thursday. Okay, that's just a few notes. Okay, let us talk about confidence intervals for means. So again, what we're going to be doing today is we're going to be saying, well, let's suppose you have collected a sample and you look at the sample mean and you have no idea what the population mean is, right? In the real world, you don't know the population mean of just about anything. So then you're going to say, well, the best guess I have for the population mean is my sample mean. But how good a guess is that? And that's what a confidence interval is going to be all about, is to decide how good a guess you have. Okay, so let me give you, this is one that you have to answer. Okay, and I'll let you know in terms of if you don't want to answer, I'll tell you what you can do instead. I have a survey question for you, and the survey question is, how old were you when you experienced your first passionate kiss? Okay. So if you've never had a kiss, maybe just state your age now and hopefully it'll happen soon. If you don't feel comfortable, then put in at least a reasonable age. Don't put 2 years old. No one has a passionate kiss at 2 years old. And just put in your data. And I'm going to type it into 15, comma, 15, comma, keep going. Everyone should be put in a number in the chat box. Keep going. How old were you when you experienced your first passionate kiss? Okay. 14, 16. There's a whole lot of you here. 15, 14, 16, 16. Okay, put it all in. Everyone should put in their number. And I've been asking the survey question for decades, by the way. So I've actually watched it and I actually have seen changes. Okay. All right. At least we got some of you. Not everyone put it in. I can't force you all to put in your numbers, but I will tell you something interesting. When I experienced my first passionate kiss, amongst all my peers, I was like really old. Everyone kind of thought I was kind of, nerdy, I guess. Um, and now I'll tell you how old I was. I was 13. Okay. And I'll let you know. In my day, it was really different. I have watched things change, and I've been collecting this data for a long time, and it has gone up. So what we have, and this is one of the things I like about this question, is I've been watching it for a while, so I've been seeing it change. Is we have this data, and again, we can't get it. We're not going to get a big enough sample size because we don't have enough people here even to get a sample over 30. So we're going to assume that the population distribution is normal. And I just want to let you know, assuming is very bad, but I have to do it for this class. But in the real world, you wouldn't do that. Okay. So that's something we're going to have to do. So now here's what we're going to do. So we're going to assume it's normal. Let's find X bar and S and N and SE. N is easy. 1, 2, 3, 4, 5, 6, 7, 8, 9. So N is 9. Let's find X bar and S. The easiest way to do that is I'm going to copy the data. I'm going to go to the calculator, one variable statistics calculator. I'm going to paste it in. This is a sample. So I'm going to click sample and I'm going to hit calculate. And the mean is 15 point bunch of ones. And the standard deviation, there's a sample standard deviation, is 0.7817. Who remembers how I'm going to find the standard error? Who remembers how to find the standard error? Hadn't been that long. This was last week. Do you remember? Okay. There was a formula using the central limit theorem. We're assuming the distribution is normal, that the standard error is the standard deviation divided by the square root of the sample size. We got lucky. N is 9. The square root of 9 is 3. Usually you don't get so lucky. So we're going to take 0.7817 and divide by 3. Does that make sense? So let me, just to remind you, let me put this in. We're in there already. So that's going to be 0.7817. Then we're going to divide by, and that's going to be the square root of 9, which is 3. And that is equal to, and I can just pop that in. So 0.7817 divided by 3. And you get 0.2605 and a bunch of sixes and a 7. I'll just copy and paste that in. Any questions? Any questions on finding the standard error? Okay, so now that we found all that, I already got that, so I don't have to put it in again. Now I'm going to draw a little picture. So what we can look at is our distribution is approximately normal. So I can draw this normal curve. Our X bar, that was about 15.11 or so. That's right here. And what we can look at is we can look at X bar minus a standard error. Now, what I want to do though is I want to look at what's called a 95% confidence interval. So what I want to do is I want to say, well, I want to be 95% confident that the population mean is within some interval. Now, if you remember, how many standard deviations out do you have to go to have 95% to be within? Who remembers that in the empirical rule? If you want 95% of the data to be within something, what do you have to know about standard deviations? How far out do you go? How many standard deviations? And in this case, standard errors because we're looking at sampling distributions. Do you remember? I don't see y'all jumping in. Okay. So remember there was a 68, 95, 99.7 law. Okay. 95% was two standard deviations away from the mean. Remember that for normal distribution? So what we're going to do now is we're going to take our X bar, 15.1111. I'll just go 1, 1 is good enough. 15.11. And then we're going to subtract two standard deviations, in this case, standard errors. Let's go 0.26 is good enough for me. So 2 times 0.26. Okay, any questions on that? And I could just pop this guy in. And you get 14.59. And that goes right here. And then I'm going to do the same thing for the other side. I'm going to add it because it's on both sides. I'm going to take 15.11, then I'm going to add 2 times 0.26. And that, I can just go and make it plus instead of minus. And I get 15.63. Okay. All right. Now that is assuming all kinds of things. So we're assuming we have a normal distribution. We're also assuming that we're assuming that we know the standard deviation, which we don't. So this is going to be approximately, but it's not going to be correct. Okay, it turns out, and this is important, that when you're doing this, we do not know sigma. Okay, all I did was make a guess at sigma. I used S because that's all I've got. So if you don't know sigma, it turns out you're going to have to do something that makes an adjustment. And it turns out that instead of using the normal distribution, we're going to have to use a slightly different distribution called the student's t distribution. This was actually developed, the person who figured this out, you'll laugh at this, it was all about beer. It happened to be a statistics instructor who also worked in a kind of a beer place, brewery, and realized that using sigma wasn't working. Okay. That probability of 95% being in there, it wasn't happening. It wasn't being 95%. It was a little bit off. And I'm not going to get into the details of the math because it's actually really hard. But this person did some math, a lot of math, came up with a new distribution, and that one worked and proved that it worked. And named it after his students and called it the student's t distribution. Okay, so that's just a note. And if you look at the student's t distribution, it looks somewhat like the normal distribution. It's just a little thicker on the left and right ends. Okay, so that's kind of the main difference. And it turns out different sample sizes give you a different distribution. With a very large sample size, it looks almost perfectly normal. With a small sample size, it's a bit off. Okay, so instead, we're going to do things a little bit differently. Okay, what we're going to do now is we have this data. And I'm going to go ahead and go back to the calculator menu. And any guess on what calculator I should use to find what we're looking for? What number? The hint is we do things in the order. Yeah, number 10. We're going to do a confidence interval for a mean. You could do it with statistics, but it's easier with data because we really have data. I'm going to do a number 11 instead because data is what we were given. Okay, so I'm going to do confidence interval for a mean with data. And then we have our data. CL stands for confidence level. And if you can have a 95% confidence level, it says enter 0.95. So you write as a decimal. I made sure I put the instructions in and I hit calculate. And notice it gives us the X bar, it gives us our S, and we get our lower bound and our upper bound are a little bit different than what we got with the other calculation because of this not using the normal distribution, which you're really not supposed to when you're doing these things because you don't know sigma. And I'm going to do two decimals, 14.51. So really, it's 14.51, comma, and it's 15.71. Let me make that much bigger. And that's the true confidence interval. Notice it's a little bit wider because we don't know the population standard deviation, so we have to kind of enlarge it a bit. We're going to say, well, we're not quite as confident as we thought. So what we're going to do, if we want to be 95% confident, you need to enlarge it. That's that whole t-distribution. The good news for you is that it's so hard that you don't have to know how to do it. All you have to know how to do is to click it into the calculator. Sound good? Doing it by hand is brutal. Okay, you can trust me. I made this calculator. Okay, any questions on that so far? All right, so the next thing we want to do, and this is really important, is we want to interpret it. So here's the interpretation. Okay, so with 95%, let me say it a little louder. With 95% confidence, we can conclude that the population mean age of first kiss among California community college students, that's our population since I asked you all, is between, and that's going to be 14.51 years old and 15.71 years old. Why did I scream the word with? You've heard me do this before when I screamed. And I put it in good old big bold red letters. Why did I scream the word with? Yeah, if you don't use the word with, you're going to lose a lot of points on everything that I ask you to write down, interpret the confidence interval. Got it? Okay, that with needs to be there. Okay, if you use AI, it's not going to have the word with. Okay, so that's just a note. Better listen to this webinar. Write it down, do what you need to do, but it's there. Okay? All right, so now the next thing is what does it mean to be 95% confident? Now, note that with 95% confidence, we can conclude the population mean age of first kiss among California community college students is between 14.51 years old and 15.71 years old. That was interpreting the confidence interval. Now we want to interpret this number 95%, what's called the confidence level. Got it? And here's how we do it. If many samples of sample size, in this case it was 9, are taken, okay? So I just looked at one sample of sample size 9, but you could take millions of sample size nine of California community college students. Okay, so if you took many, many, many of them, then each one will result in a different confidence interval. 95% of these confidence intervals will contain the true population mean age of first kiss. The other 5% will not contain the population mean age of first kiss. Okay, so imagine you're in the business of looking at data and then publishing it, maybe announcing it in the news. Then if you're going to do a survey and you're going to make an announcement, you want to be right most of the time, right? If you're wrong most of the time, everyone's going to laugh at you and they're going to say you're stupid. So you want to be right most of the time. And our definition of most, okay, and this is for kind of general studies, is 95% of the time. Okay, and actually, you probably would never guess who chose the 95% as the one that everyone uses now, or not everyone, but a lot of people use it. And this is when you have to know a little history. This was done almost 100 years ago, actually. Think about 80, maybe 90 years ago, 85 years ago, I think. Um, so think about who was doing this stuff a lot. Okay, definitely was not the internet that many years ago. Any guess? So who was announcing things to the public all the time? Okay, maybe you won't guess, but let me tell you, the New York Times. So the New York Times was like the main news group in the nation. And they're the ones that decided 95% is the right way to go. And they'll be happy, they'll be okay being wrong 5% of the time, if they're right 95% of the time. And they made that decision and everyone's gone with it. Okay. And that doesn't mean that you always want to use a 95% confidence. Okay. When you're doing news, pretty much always use 95% confidence. When you're doing anything in social science, you pretty much always use 95% confidence. When do you think you want to be a lot more than 95% confident? Can you think of an example or a field where you want to be more than 95% confident? Any thoughts? Business? If you got a 95% chance of doing well in your business, that's good enough. Yeah, there's a lot of medical clinical studies. A lot of medical clinical. If there's a 5% chance that you're going to kill someone because of what you're doing, and maybe all you're doing is, I don't know, making their face look a little prettier, then you want to be more than 95% confident. You don't want a 5% chance of killing a lot of people. Does that make sense? So medical, often you're going to use higher than 95%. It turns out less than 95%, like 90%. That one you often would use, say, I personally use it I call it business, but really it's stock market, for example. If I can have a good win, make a lot of money 90% of the time of the investments that I make in the stock market, I've done really well. Does that make sense? So that would be one where 95% you can go a little lower than that. Does that make sense? So sometimes you want to go higher, sometimes you want to go lower. News pretty much always goes 95%. Social science, psychology, sociology, all that pretty much always goes 95%. Any questions at all on this? All right, so here's a template. Okay, so use this template and then when I write XXX, don't put XXX in, it's whatever your confidence is, with whatever percent confidence. It can be concluded that the population mean of whatever you're talking about, in our case, it was age of first kiss, is between whatever and whatever else. So it's the low and the high. And that's a good template so you know what to write. So I'll make sure I leave it up there so you can take notes because that'll help you. And this works pretty well. Okay, there are some other ways of writing it, but you have to start with the word with in this class. Any questions on this conclusion template? Okay, so let me give you the next template, which is interpreting the confidence level template. Oh, yeah, writing it like that, then you'll get more points. Okay, so the confidence, if many samples are taken, if many samples of whatever your sample size was taken, then each would produce its own confidence interval. Whatever percent, so it might be 95%, of these confidence intervals will contain the true population mean of whatever you're talking about, and whatever one minus that percent won't contain the true population mean. Any questions on that? Okay. Just a note that you still need a sample size over 30 if you don't know the population distribution is normal. Okay, so always a good idea to get over 30 so that, 31 is the minimum in our class. It's a little more complicated than I'm saying, but for our class, we're going to make 30 over 30 is what you have to have. Any questions on that? All right, so now that was means. That was when the survey question, right? All of you answered with a number. It was 15 or 14. Okay, some of you answered 13. But sometimes it's a yes/no survey question. So now what we want to do is we want to move to proportions. So here's a question I have. What percentage of adult Americans see the need for a third party? So right now, hopefully you know our main parties are Democrat and Republican. Okay, so a study was done by Gallup, actually, asking people, do you see the need to have a third party? Or are you fine with having two parties being the main thing in America? Does that make sense? And if they ask you, let's see if you can put in the chat box. What do you think? Do you see the need for a third party? Pop in your answer. Okay, so you'll notice nobody put a number in. You're not going to say 73. You're either going to say yes or you're going to say no. Does that make sense? So this is a yes/no question, which means we can't use what we just used. Okay, I will give you the data that Gallup found, and that is they actually surveyed 1,000 people. I researched it. Okay, I read the article, and they found that the p hat, which is a sample proportion, was 0.62. So 62% of the people that they surveyed, of the 1,000 people, said yes, there's a need for a third party. Okay, and the rest said no. Okay. So the number of yes answers, if you take 62% of 1,000, that one I can do in my head. You might be able to also. That's 620, which clearly is greater than 5, a lot greater. NP is what's left over, and that'll be 380. Sorry, whoops. NP, number of yes answers was that. So that was the NP was 620. The number of no answers, that was the 380. That's our NQ, and that is certainly greater than 5. Okay, by a lot, which means that the normal distribution central limit theorem definitely applies here. We can use the central limit theorem. And that means that we can do this. If you have a sample size that's too small, and either NP or NQ is not greater than 5, then this doesn't work. Okay, you just need to survey more people. Okay, but Gallup surveyed definitely enough by plenty. All right, now let's find a confidence interval. How do you think I'm going to find a confidence interval? Any guess? I don't see jumping in. I'm going to go to the calculator. This calculator will not work the one we're looking at. Why will this not work? Why is this calculator not going to work? The one we're looking at, which is the confidence interval calculator with data sigma unknown. Don't see y'all jumping in. Okay. This is when you have data. This is when you have numbers. This is quantitative. We do not have a quantity. There is no sigma. We don't have a quantitative survey question. I can go back to the calculator menu. And now what calculator should I use? What number? Um, it's not 10. We're not looking at a mean. It's not 11. That's for a mean also. Those don't work. This is a yes, no survey question. Yeah, it's 13. Confidence interval for a proportion, because we're talking about a proportion now. It's a yes, no question. So I click on confidence interval for proportion. Now it says fill in the sample size, the number of successes, and the confidence level. Write down the confidence level as a decimal, etc. So our sample size, or their sample size, was 1,000. The X, that was the number of yeses. That was 620. Confidence level, let's use 0.95. Any questions on that? Okay, this is definitely kind of a sociology newsy thing. So 95% makes the most sense. And hit calculate. And there we go. Gives the lower bound, it gives the upper bound. It gives our p hat, which was 62% better. It also shows a picture. You can see. Okay. And again, you have an approximate normal distribution. And there we go. Okay. In this case, by the way, we're not guessing at a standard deviation. So there's no student's t-distribution issue here. This truly is just a normal curve we're looking at. Any questions on that? Whereas when you had the confidence interval for a mean, you needed to use the student's t-distribution because you don't know sigma. Here, there is no sigma to know. Okay, any questions on that? All right, so our confidence interval, I'll use the two decimals, 0.59 and 0.65. Will be our confidence interval. Just a note, and this is important, something called the margin of error. The margin of error is how far the bounds are from the center. Okay, and any guess on the math I'm going to need to do? It's very simple math, but any guess on the math I'm going to do to find out how far the confidence interval is from the center? It's kind of two choices. I don't see jumping in. Okay, if you're not given the p hat, then what you do is you add the numbers and then divide by 2 because the average of the left and the right will give you the middle because we have a normal distribution. Normal distribution is symmetric, so the average is in the middle. So what I can do is I can do 0.59 plus 0.65 and divide by 2, which is 0.03. Okay. Notice that you can also say how far is 0.65 away from 0.62, and that's 0.03. You can see the same answer. So if you happen to know p hat, sometimes that's a little easier. Okay, and that's called the margin of error. And sometimes they'll say plus or minus 0.03 because it goes in both directions. Any questions at all on the finding the confidence interval and the margin of error when we're talking proportions? Any questions? Okay, let's interpret this confidence interval. I want you to type in the first word that we should put in the interpretation. Yeah, with. So here's the interpretation. We start with 95% confidence. We can conclude that the population, note now it's proportion, it's not mean, the population proportion of all adult Americans who see the need for a third party is between 0.59 and 0.65. Any questions on how that's written? Okay, it turns out there's kind of another way of writing it also, which is still going to start with the word with, but you can also say with 95% confidence between 59% and 65% of all adult Americans see the need for a third party. It means exactly the same thing, and it might be for a lot of people, it's easier to think about that it's between 59% and 65% than the proportions between 0.59 and 0.65. It means the same thing though. Any questions? Any questions on the interpretation of this confidence interval? Any questions? Okay, now let's interpret the confidence level. And it's going to be very similar to what we saw in the last example. If many groups of 1,000 adult Americans are surveyed, notice it starts the same way, same idea, then each group will result in its own confidence interval. 95% of these confidence intervals will contain the true population proportion of all adult Americans who see the need for a third party. And 5% of these confidence intervals will not contain the true population proportion of all adult Americans who see the need for a third party. So, in a way, if you're in the business of creating confidence intervals, so you do a lot of the statistics and you maybe you're, a media person, and then 95% of the time when you cite a confidence interval, hey, the mean really is going to be in there, or the proportion is really going to be in there. And 5% of the time, you're like, uh-oh, I got it wrong. Okay. And again, all this assumes that you did everything randomly, so it doesn't mean you made a mistake. It just means you had bad luck. Because when you're talking about, conducting a survey and collecting a sample, even if you do everything right, sometimes you could be off by too much. You just get bad luck. Does that make sense? Um, oh, true. So this is the true pot. So the idea is the best estimate for the population proportion that we had in this example was 0.62. That's not the true population proportion. That's our best estimate for the population proportion. The true population proportion is the actual one, but we'll never know what that is. Do you see? But we can say that we're 95% confident that it's between 0.59 and 0.65. But we don't know for sure, and we don't even know, say it's between, we don't know exactly where it is. Do you see that? So again, there is our estimated value. That's this guy, 0.62. Then there's the true population proportion, and that's the one you don't know. And it's impossible to find it because you can't survey every American adult. Good luck. Not going to happen. Okay, but there is a population proportion. We just can't know it. It's just too big a population. Any questions on that? Okay. And sometimes you want to look at that. You know, if you found out, for example, a 95% confidence interval for the proportion of, say, aces that the dealer has when you're playing blackjack against the dealer, and you do an estimate and you find out that it's between 40% and 60% of their cards are going to be aces, what does that tell you is probably happening? So if your confidence interval was between 40% and 60% of all the dealer's cards are aces, what's probably happening? Yeah, cheating. Okay. And when I was younger, when I was 21, that happened a lot. And what I would do is I would use the statistics. I do some analysis. I do a little more complicated analysis than I can mention now. We'll get that later. And if they were cheating, do you know what I would do? So if it was way outside the confidence interval, the 1 out of 13, which is what it really should be. No, 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 you don't cheat back. No, you leave. You leave. In those days, it was run by the mafia. You cheat back, they kill you. I'm not kidding. Yeah, don't cheat back. Okay. Nowadays, there's not much cheating going on. That's the good news. Okay. Any questions on that? And I was a card counter, so I used to do that kind of stuff. Okay. I didn't cheat, but I would detect the cheaters and leave if they were cheating on me. All right. Any questions at all on these examples? All right. I'm going to give you the secret word a little earlier this time. We still have a lot more to do, though. That way, someone who's not watching isn't they're gonna look at the end and not see it. The secret word is with, because that is the important word. That is the important word for confidence intervals, because that's the first word that you should use when you're interpreting the confidence interval is the word with, not the level, but the interval. So with is the secret word for the week 6 secret word. Okay. Now let's move on to the next question. All right, now it's time to think about the sample size needed for a mean. So the first thing is that I want to remind you the central limit theorem states that sigma sub x bar, that was the sampling, that was the standard deviation of the sampling distribution, also called the standard error, was sigma over root n. Okay, so E, the error, is going to be our z-score times sigma sub x bar, which is z sigma over root n. And now you don't have to do the math, but I'm going to tell you, you just multiply by root n, divide by e, take a square of both sides, and you get n equals z sigma over e quantity squared. Okay? And that's the formula to say how big a sample size do I need so that my error is what I want it to be, or maybe no more than what I want it to be. Does that make sense? Okay, we're also going to have another way of doing it, but I want to show you this because the math isn't that bad. We're assuming that S is approximately sigma. Okay, so here's an example. Let's suppose you wanted a margin of error of no more than 0.5 years old, okay, for the age of first kiss. Got it? How large a sample size would you need? Okay, and let's remember a couple things. One is we want the error to be no more than 0.5. Okay? We're going to estimate our standard deviation way up here to be 0.7817. That's our best estimate. It's as good as we can do. And that's often what you do is you do a small sample. That's your best estimate for the standard deviation. And you use that to say, now how big a sample size am I going to really need? All right, so there's two ways of doing this. One One is to plug in to the formula, but then I made an easier way, and that is the calculator. So what calculator number do you think I want to use now? Yeah, 12, because I want the sample size, and we're talking about a mean, because it was a quantitative survey question. So then I go here, and sigma, remember, was 0.7817. We wanted the error to be a half year old, so within a half a year. And we wanted again to find a 95% confidence. Okay, because that's what we're looking at now. So 0.95 and hit calculate end. Okay. And in that case, 10 is good enough as long as you know you have a normal distribution. Does that make sense? Okay. If you didn't know you had a normal distribution, you got 10, then you'd say 31. So if you want a margin of error of no more than 0.5 years old, how large sample size? You survey 10 California community college students. Okay. All right. Now let's do another one. Let's suppose you wanted to find a 90% confidence interval for the population mean hourly wage of nurses in California. Okay. Based on a preliminary study, the standard deviation is assumed to be $25 an hour. Notice this is a standard deviation. This is not how much money they're making. This is how much they vary from one nurse to another nurse. Does that make sense? On average. If you want the margin of error to be no more than $2, how many nurses must you survey? So let's use the calculator again. I just go ahead and same calculator will work. Now our standard deviation was 25. We want the margin of error no more than $2. And we're okay with a 90%. And they calculate in. We need to survey 423 nurses. Okay, which is a lot of work, by the way. And you might say, oh boy, I need funding for this one. Any questions on what I just did? Okay, I will let you know there have been some faculty at other colleges who are mad at me for creating this calculator. Any guess on why? Actually had some faculty, say, no, you can't do that. Here's a hint. The students aren't angry, only the faculty are. I don't hear you, so let me tell you, because it's too easy. Some faculty want you to use the formal algebra formula, but we're going to use this. Sound good? Okay, so that was an example, and it's really important. Okay. All right. Now let's suppose we want to find the sample size needed for a confidence interval for a population proportion. Okay. In this case, with population proportions, if you quantitative data, if you have no idea what the standard deviation is, you can't even make a good guess. It turns out with the yes no survey question, there is a good guess if you don't know the population proportion. On the other hand, if you do know, or if you have a good guess of the population proportion, then you can actually do better. So let me show you an example. Okay, suppose you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. Let's suppose you want a margin of error of no more than 3%. How many cars must you look at? Okay, notice the survey. This is a yes, no survey question because the question I would ask you is, is your car an electric vehicle? And what would you say? Or do you have an electric vehicle? Or I'd look at someone who had a car and say, do you have an electric vehicle? And they're going to say yes, or they're going to say no. Does that make sense? So this is definitely the yes, no type question. Okay, which means that this calculator won't work. So I can go back to the calculator menu and let me ask you, what do you think I need to go to now? Which calculator? 10 would be confidence interval for a mean with statistics. First thing, it's a yes, no question. Second is not, we're not looking for a confidence interval. So it's not number 10. Yeah, it's 14. Because we want to find a sample size and we have a proportion. It's a yes, no survey question. Do you see? It's very important to know which calculator to use, otherwise you're not going to be able to do any of this. Okay, so then notice there's two choices. Either you have no estimate for proportion or you have an estimate. So for our example right here, part A, do we have an estimate for the proportion of cars that are electric vehicles? What do you think? Do we have an estimate? Yeah, there's no estimate. Nothing in here tells you what proportion of all electric vehicles, of all cars are electric. Okay, so we don't have an estimate. Okay, so you're going to click on no estimate for P. Your margin of error, that's E. We wanted no more than 3%. So that's going to be 0.03. The confidence level that we want was 99%. So that's 0.99. And I calculate N. That means we need to survey 1,844 people who own a car to ask them if they have an electric vehicle or not. Okay, that's a lot of work, isn't it? Okay, let's look at part B. Let's suppose you looked at last year's data. And last year, which I looked online, by the way, 8% of all cars were electric vehicles. How many cars would you need to look at for the 99% confidence interval? How is that different this time? What do I have to do now? Yeah, now we have an estimate. So click on have an estimate for P. And now you'll notice there's a new tab in here, estimate for P. And the estimate for P, if you see, was 8% or 0.08. And in this case, everything else is the same. We still want a margin of error of 3%. We wanted a 99% confidence interval. So we calculate N. Notice it's much smaller, 543. Made a huge difference. When you have an estimate for P and that P is either very low or very high, then it really matters. So if you're thinking about, maybe you have a business to do, collect data, it's a lot less costly to survey 543 people than over 1,800 people. Makes a big difference. Does that make sense? Okay. Just a note, if you don't have an estimate for P and you wanted a 3% margin of error and you wanted a 95% confidence interval, it's a little more than 1,000. And that's pretty standard. So you'll notice that when you read these articles, when there was a yes no survey question, many, many, many of them surveyed around 1,000 people because that's kind of the standard because that will get you a 3% margin of error, which is kind of what people want nowadays. Okay? Not everybody, but that's a typical thing they want. So you'll often see around 1,000 for the sample size when you look into research stuff. Any questions at all about sample size calculator, about finding the sample size for either a mean or a proportion? Any questions? Okay, it's very important because again, you want to decide how many people you need to survey. If you survey too few, then you're going to have a ridiculous confidence interval. If I surveyed, just a few people and asked, for say, I don't know, maybe average weight, and I said I'm 99% confident that the average weight of adult, people in America is somewhere between 30 pounds and 500 pounds. Okay? You can be very confident of that. But if you found anything interesting, if I say I'm 99% confident that the average weight is between 30 pounds and 500 pounds, you have useless data. Does that make sense? Because of course it's between that. It's not telling you anything. So that's why you want to decide what your margin of error is, and then decide on how many people you need to survey. And then you'll have good data. Whereas if you don't survey enough, then you're going to have a confidence interval that is pretty useless. What's the problem with surveying too many? Any thoughts? What's the issue with surveying too many? Yeah, it's a waste of time, and in the real world, it's a waste of money because for a big sample, you often have to pay people to do it. Does that make sense? Pay people to conduct the survey. So it could be a waste of time, it could be a waste of money. Sometimes that waste of time could be really horrible. For example, if it took 10 years to get reliable data for deciding whether the COVID vaccination was helpful, that would have been really bad, right? Having that vaccination really made a difference in the world. And that would be a terrible waste of time if they ended up wanting to survey a million, do 1 million people for the trial, then it would have been horrible. Do you see that? Because it might have taken 10 years to do that. And by then, COVID would still be around for 10 years in, horrible, killing times. You don't want that. Does that make sense? So again, if you have too big a sample size, it could be too much time or too much money. If you have too small a sample size, then you're going to have a margin of error that's too big to actually give you any information that's helpful. One more thing, and that is, as I mentioned, with the 95% confidence level, it was around 1,000 people. You say, well, maybe I'd rather be 99% confident because, you want to be more confident, right? What's the problem with being 99% confident? What's the issue? Okay. The issue is two things. One is that sometimes it means that you have to survey a whole lot more people. Any questions on that? But let me show you what else it could mean. If we go back to the confidence interval for proportion, and remember with the 99, let's go for means actually. Let's do that example. I think that's even better. If I go confidence interval for a mean, let's go back and let's go with data. And let's pop in that data. Our sample size was 9. That can't change. So if I wanted a 99% confidence interval, then now notice the lower bound is 4.24 to 5 point, so now it's like 14.2 to 16. And what ends up happening is you get a wider margin of error. So yeah, you could be more confident, but then you have a margin of error that's wider and it may not be as useful. May not tell you much. Does that make sense? Whereas if I want a smaller margin of error, but I can't change the data or anything, I could go to a 90% confidence interval. And then I get 14.6 to 15.6. Okay, which is actually better, right? You get a smaller margin of error. But then you're only 90% confident. And that means that, if you're doing a lot of statistics, then 10% of the time, it's going to be wrong. Do you see? And maybe you're not happy to be wrong 10% of the time. Yeah, you get your margin of error smaller, but you can be wrong more often. So you have to look at the pros and cons of the 90%, the 95%, and the 99%. And I'm going to let you know in our class, those are the only three we're going to use. 90, 95, and 99. Got it? Okay. And again, this is elementary stats, so I don't want to get too technical. So we're going to stick with those three. And 95% is the standard. Yeah, 90, 95, and 99. 95% is the standard. And I could ask you the pros and cons of 90%, 95%, and 99%. And you have to decide. And sometimes you just look at all three confidence intervals and say which is best for whoever you're doing it for. Does that make sense? And again, the pros are going to be you have a smaller margin of error with the 90%, say the pros for the 90%, but the con is that you have a bigger chance of being wrong. For the 99%, the pros are you have a very small chance of being wrong, but the con is your margin of error is bigger. So you have to decide, is that margin of error too big, or are you still okay with what you have with the 99? And then you choose the 99. Do you see? So I'm going to be asking you that, and I will let you know. And it's a little early, but I'm going to tell you in project 2, you're going to have to do that. You're definitely going to have to state the pros and cons and look at all three. And based on the pros and cons, after looking at the three, you're going to have to decide which is best for the client. Any questions on that idea? Okay. I'm going to tell you, you're probably going to be happy about this, but maybe not. I'm not seeing a lot of questions, but we're going to end a little earlier than usual because we've kind of covered everything I need to cover. But that doesn't mean I can't answer more questions, but I think I'm going to stop the video and remind you do have an exam this week, so don't forget. Don't wait till Sunday night, by the way, because then internet could go down. Then you're screwed. I would do it a little earlier. Okay. Okay. You want to be at least 99% sure that everything's going to be good. Look at that. So that's just a big note. Yeah, we don't want another AWS outage. So if you do it by Friday, then hey, you got it. And hey, if you try to do it by Friday, it doesn't work, you can ask for more time. You could even do that. Okay. So I am going to stop the recording and thank you for watching this. And again, I'm always afterwards happy to answer any questions you have.